Welcome back everyone. In the last video we took a look at a 386 based PC104 single board computer called the TS3100. It was a low-end DOS computer meant for replacing PCXT and PCAT based computers for embedded applications. I had a rather unusual problem with them where replacing the RTC module triggered a bug in the BIOS which caused it to erase itself, so we're exploring how to create a recovery tool that replaces the BIOS to let us reprogram the onboard flash. Today we're going to check out DOS programming in 16-bit x86 assembly to get familiar with how to write software for these old CPUs before we ditch the BIOS. And without further ado, let's jump into it. DOS is a 16-bit operating system and along with its programs operates in what's called real mode. This was the operating mode of the 8086 and 8186 processors and is the initial startup mode on the 286 and all future x86 processors for compatibility reasons. But what does this actually mean? Regardless of whether you have a 16, 32, or 64-bit CPU, all registers are treated as 16 bits. You also only have access to the base set of 8 general-purpose registers. There are exceptions, but for simplicity's sake, we'll ignore that for now. Under real mode, the total amount of address space is 20 bits, or a single megabyte. There are no privilege levels or memory protection. Regardless of whether the CPU is running operating system code or user code, programs have total control over the CPU at all times, and there's nothing preventing a malfunctioning or malicious program from accessing memory owned by other parts of the system. There is also no address translation of virtual memory. All memory accesses are done with physical addresses, hence the name real mode, which is short for real address mode. Now you might be asking, if the registers are 16 bits, how do you form a 20-bit memory address? Real mode uses a technique called segmentation. In addition to the 8 general purpose registers, there are 4 16-bit segment registers called the code segment, the data segment, the stack segment, and the extra segment. Memory accesses either implicitly or explicitly take one of the segment registers, multiply it by 16, which is a binary left shift by 4, and then add to it whatever addressing mode was used to form the 20-bit address. In effect, each segment register defines a 64 kilobyte window into the 1 megabyte address space, and programs can move these segment registers around at will. While Intel calls the 8 primary registers general purpose, like many architectures of the day, they all have specializations, as some instructions can only use certain registers. First, we have the AX register, or the accumulator register. Instructions with the AX register typically have a shorter binary encoding and are thus faster. It, along with the DX register, depending on length, forms either the multiplicand or dividend, along with the result register and multiplication or division instructions, and is the only valid source and destination register for I/O and string instructions. Next is the BX register, or the base register. It's one of a few registers which can be used for the address of an indirect memory access, dereferencing a pointer. Accesses using BX are implicitly performed in the data segment, although this can be overridden with any other segment register at the cost of a larger binary encoding. Then we have the CX register, or the count register. It's used for operations where a count is required, such as a variable length shift, loop, or string instruction. There's the DX register, or the data register. It's used for the address and indirect I/O operations, the upper word of the product of a 16 by 16 bit multiplication, the upper word of the dividend in the 32 by 16 bit division, and the remainder also in the 32 by 16-bit division. Next is the BP register, or the base pointer register. Like BX, it can also be used as the base address of an indirect memory access. This register is typically used as the pointer for a function stack frame, and accesses are implicitly performed in the stack segment. And again, like BX, this can be overridden. Then we have the SI register, or the source index register. It can also be used for indirect memory accesses as well, or additionally be combined with either of the base registers for base plus index indirect addressing. It's also used as the source pointer for load and move I/O and string instructions. Accesses are performed using the segment register associated with the base register used, or if used alone, implicitly uses the data segment. Then there's the DI register, or the destination index register. It, like SI, can be used for indirect memory accesses and be combined with the base registers for base plus index indirect addressing. It's also used as the destination pointer for store and move I/O and string instructions, and the source pointer for scan string instructions. When used with I/O and string instructions, it implicitly uses the extra segment. Finally, there's the SP register, or the stack pointer. While arithmetic and move instructions can be performed on the stack pointer, it otherwise can only be used with the call, return, push, and pop instructions. Unsurprisingly, accesses are only performed using the stack segment and cannot be overridden. Now, I recognize that this is a boatload of information to digest in 5 minutes? Let's jump into some actual examples. But before we get started, I need to give a bit of a disclaimer. We're going to be writing code for real mode, the operating mode of the very first x86 CPU. x86 is only a few years away from being a 50-year-old architecture. While modern x86 processors can still run code meant for the original 8086, it's hard to articulate how fundamentally different the modern processors are. It's quite likely that every programming choice you see me make represents the wrong way of doing things now, or heck, even just a few years later. The level of compatibility is something truly amazing. The fact that I can natively execute programs compiled 50 years ago on the 16-core machine I'm editing this on, or on the 128-core monster that's running the cloud service you're watching this on is nuts. I don't envy the microcode engineer that has to make sure that MS-DOS boots correctly on a modern server CPU. It's a feat of compatibility only bested by IBM's mainframes, which can still natively run software written for their System 360 machines from the mid-1960s. But anyway, in order to build our DOS executables, we're going to use an assembler called NASM. NASM is a modern assembler that supports literally every x86 processor ever made and runs on pretty much anything. While it might not be quite as popular as the GNU assembler, it has some nice quality of life features for when you're writing complex assembly programs. But how do we write DOS executables using modern tools on Linux, you say? Well, we're not going to be writing anything particularly complicated, so we're going to abuse a DOS executable format called COM. And to be honest, you can be hard-pressed to call COM a format at all. It's literally just a dump of memory. When you run a COM executable, DOS finds the first free contiguous 64 kilobyte block of memory, takes all of those segment registers we talked about and points them at it, points the stack pointer to the end, sets up some housekeeping information, copies the file into it starting at 100 hex, and finally goes and jumps to 100 hex. So the first byte of your COM file better be executable or else all hell is about to break loose. Jumping into the assembly, the first thing we do is use the bit statement to tell the assembler we're targeting 16-bit mode, and use the organize statement to tell the assembler that the statements following will start at that 100 hex address the COM executable will be loaded to. In keeping with tradition, the first program we'll write is Hello World. This is just a simple program that prints the text Hello World to the console to demonstrate that your tools are working. Using a label, which in NASM is any text followed by a colon, we'll call our function main. We're then going to need to find some method to write text to the console, and then we're going to need to find another method that lets us exit the program. We then need to define our hello world message. We use the define byte statement and write hello world in quotes to define a string, followed by a 10 for a new line and 13 for a carriage return. You might be used to using just a new line, but on DOS you need to use the full CRLF ending. Editing note, it should be 13 followed by 10. It doesn't seem to matter for printing to the console, but it would probably confuse a text editor. Next, we define the length of our message using the equate statement. The $sign returns the current address the assembler is at, so if we subtract from it the location of the beginning of the string, it gives us the length. The cool thing about equate is that this value doesn't actually end up in the binary file, it just creates a symbol that's equal to that value. It's a compile and link time constant. Now that we have our message, let's figure out how to print it to the screen. One of the basic functions of an operating system is to provide abstractions for accessing input and output devices. Despite DOS hardly being an operating system at all by modern standards, and honestly even some standards of the time, programs in DOS do have the concept of standard input and standard output. These are generalized streams of data coming from an input device like your keyboard and data going to an output device like your screen. So to print our message, we need to write it to standard out. In order to tell the operating system we needed to do something, we need to perform what are called system calls, which on DOS are provided by software interrupt 21 hex. If you've spent much time writing drivers or using microcontrollers, you probably primarily think of interrupts as something triggered by hardware when it needs attention. Say a timer expiring or a UART receiving data. Some architectures such as x86 also support triggering interrupts from software, but why would you want to do this? Even though real mode doesn't have memory protection, our program doesn't know where the operating system's syscall handler actually is, so interrupts are used as a form of indirection. The OS writes the address of wherever it's placed the handler into the interrupt table, so all our program has to know is what interrupt number to call. If we look at the syscall table for DOS, we can see that there are a few functions for writing to standard out. This one writes a single character at a time, and this one writes a string. It could work, but it uses a $sign to mark the end of the string, which is a printable character, so let's keep looking. Okay, write to file or device, this is promising. Set register AH to 40 hex, BX to a file handle, CX to the number of bytes to write, and DX to the buffer. COM executables by default have all of the segment registers set to the same block of memory, so we don't have to worry about changing the data segment unless we need more than 64 kilobytes of memory, which we won't for any of these simple examples. Alright, so when a program is started, DOS opens 3 file handles by default. Handle 0 is standard in, handle 1 is standard out, and handle 2 is standard error, which was probably inspired by Unix using file descriptors 0, 1, and 2 for the same streams. I forgot to mention it before, but registers AX through DX can be subdivided into 2 8-bit registers each. AX can be divided into AH, which is the high byte of the register, and AL, which is the low byte of the register. BX is subdivided into BH and BL, and so on. So we'll start by setting AH, which is the upper byte of AX, to 40 hex by using the move instruction, and then set BX to file handle 1 for standard out, CX to the length of our message, and DX to the address of the message. Then we finally call interrupt 21 hex to perform the write. And now we need a way to exit the program. Looking back at the system call table, we find that function 4c hex exits the program, and we put the return code in register AL. Anything XOR to itself is 0, so we can use XOR AL to set AL to 0, and then we set AH to 4c hex and call interrupt 21 hex. And that's it. Dropping back to the terminal, we can assemble the program using NASM followed by -fbin to output a binary file, We'll output the file to hello.com, and then our source file is hello.asm. That leaves us with the com file, and we can see that it contains some object code and our message. Now if we copy that to our single board computer and run hello.com, it prints out hello world. If you're coming from high-level languages, there's a footgun in assembly that might not be super obvious. Without giving any other information to the assembler, it will assemble from the beginning to the end of the file in that order. All the org statement does is change the run address of the code. It doesn't change anything about where that code is in the file. So if we were to move our message declaration to the beginning of the file and reassemble it, the assembler doesn't report any errors, but looking at the binary, you can see that the message data is now at the beginning of the file. If we were to try and run this, the CPU would try executing the data of the message as if it were code, as it doesn't know any better, and that would almost certainly cause problems. We can get around this by dividing our code into sections. Canonically, read-only data is placed in a section called .ro data, and code is placed in a section called .text. By default, the assembler will put the contents of the .text section at the beginning of the binary file. Rerunning the assembler, we can see that the code once again is at the beginning of the file, and the message comes after. With that fixed, let's extend our hello world program to print the message in a loop. We can go back to main using the jump instruction, but if we leave our program like this, it'll just run in an infinite loop, so let's tell it to exit the loop when a key is pressed. Looking at the system call table, there's this function that reads a character from standard in, but it'll wait until a key is pressed. We don't really want to wait, we just want to know when one is available. Here's what we want. Function 0b hex checks whether a character is available. It takes no arguments and returns 0 in register AL if there's no character, and ff hex if there is one. So let's call that function. We can then use the test instruction to check if register AL is 0. Test performs a bitwise AND of the operands and sets the status flags according to the result. Anything ANDed to itself is just itself, so if all of the bits in AL are 0, the processor's 0 flag will be set. So if the 0 flag is set, that means no key has been pressed and we should jump back to main. And let's just delete that infinite loop. If there was a character available, we should be kind and read it from the input buffer before exiting. And if we look back at the syscall table, we can see that function 8 hex will read the character in the buffer without displaying it to the screen. So let's just call that function, and we don't actually care about the result, so we're done. If we assemble the program and copy it to the computer, we see that it just prints hello world over and over until I press a key, and then it exits. But notice that if I press Ctrl-C, the program doesn't exit like you'd expect it to on a modern system. If something were to have gotten stuck, we couldn't do anything about it. If we comment out checking for a key and just let it loop infinitely, you can see that we're actually stuck. It doesn't respond to input anymore. There's nothing we can do other than forcibly restart the system. As DOS is a single-tasking operating system, we have to register our own Control-C handler so that the computer knows what to do if it's pressed. According to this note on the character input function, that's interrupt 23 hex. Yeah, we actually have to point one of the CPU's interrupts into our user program. There is a DOS system call to set interrupt handlers. Function 25 hex lets us set up an interrupt vector to point at our program. Now, these vectors can be somewhat tricky. Normally you'd have to back up the previous vector and restore it before exiting, but a few, like the Control-C handler, are automatically restored upon exit. So before our main function, set register AL to 23 hex for the interrupt number, register AH to 25 hex for the function number, register DX to the exit function at the end of our program, and call interrupt 21 hex to set the vector. And don't forget to uncomment the code that checks the input buffer. Assembling and running our program, we can now exit the program by hitting a key or by pressing Control-C. Looking back at our program, it's starting to get kind of long, and there's not really any functional separation between its parts. If you've used high-level languages, you'd normally expect main to be a function that gets called with the environment ready to go, and to exit you would just return from it with the status code. For a C program, this is handled by the runtime, but we don't get one of those here, so we have to write it ourselves. So what would that look like? Well, let's start by turning main into a function. We'll have it return the status code in register AL, so let's zero out the AL register and put a return instruction after we read the final character from standard in. Back at the beginning of our program, we now need to make a subroutine call to main after setting up the Control-C handler and move the exit function up from the end of the file to after calling main, so that when main returns, the program exits. Remove the previous XOR zeroing of register AL so that we exit with whatever status code main returned, and let's leave a comment reminding us that the entry point is essentially our Control-C setup call. And after that, the program still assembles just fine. But now we're mixing our runtime definition with our main program. Ideally, we would just need to write a main function and not worry much about the runtime. So let's move the runtime into a separate source file. Let's copy our main file to rt.asm and delete anything that isn't startup or exit code, and similarly remove the runtime code from our main file. But now we have a bit of a problem. NASM can only assemble one file at a time, so while we could include our runtime source code via the preprocessor, it's generally bad practice to include source code that way that could otherwise be separated into its own source file. That means that rather than outputting our program directly from NASM as a binary, we need to output in a format we can use with an external linker, and the most suitable here is ELF. But when we try to assemble, we get a parser error on the org statement, so we need to remove it, and the same goes for our runtime file. But now we get an error about main not being defined, which makes sense because the rt.asm file has zero knowledge about our main assembly file. Back in our main file, we need to mark main as a global symbol so it'll be available during linking, and we also need to add an extern main statement to our runtime so that it knows there will be an external symbol called main. Now both files assemble just fine. Since we've output both as ELF files, we can use the object dump command to inspect the generated code. We can see the bytes of our message in the RO data section and the bytes of our program in the text section. If we check the runtime, we see the same thing. Although, let's put a nice label at the beginning of the runtime so we get something other than exit minus hex 0c. Perfect. Now let's try to run the linker. Output the binary file is hello.com with the two object files we assembled and incompatible with x86-64. Well, that makes sense. Let's specify the i386 linker. And it failed again. Essentially what's happening is that the linker doesn't have any idea where to place the code we've assembled, and none of the defaults for 32-bit are working because we're trying to link 16-bit code. To fix this, we need to write what's called a linker script, which tells the linker where to place things. We start by writing .=100 hex, which sets the run address to 100 hex. This has the same effect that the org statements did previously. Now we define the output binary's text segment as every object file's text segment concatenated. The asterisk represents a wildcard match of the input object's file names. We then write .=line 4 to set the run address to the next address that's divisible by 4. x86 only has an alignment requirement for the stack, but it's good practice to align everything to the processor's largest register size. And finally define the output binary's read-only data section. While we're currently operating in 16-bit mode, our board does have a 386, which is a 32-bit processor. And the reason I say largest register size is that the Pentium MMX added 64-bit registers for the MMX functionality, and the Pentium 3 added 128-bit registers with SSE. While both of these were 32-bit CPUs, they required up to 16-byte stack alignment to store MMX or SSE registers on the stack. Now if we pass the linker script when linking, we actually output an executable. Although if we look at the binary, it looks like we have a problem. B4 hex 40 hex is the instruction for moving 40 hex into register AL, which means that the main function is at the beginning of the executable and not the runtime entry point. If we output the executable as an ELF file rather than a binary file, we can inspect it with object dump again, and yeah, it put main at the beginning of the binary. There's a couple of ways we could fix this. We could go with the brute force method of specifying that the runtime object file's text section comes before the main file's text section. And that does work, but it isn't elegant. We don't want to have to write every object file's name into the linker script, so how about instead we create a special init section that we define only in the runtime as a jump instruction to the beginning of the runtime. Now all we have to do is put the init section before the text section in the linker script and everything should work again. After reassembling and linking, the linked code looks good. There's a jump instruction to the start of the runtime at 100 hex. If we copy the executable to the board, it still runs as expected, and still exits on a key press or Control-C. As we add more assembly files, it's going to get progressively more unpleasant to compile everything by hand, so let's write a makefile to automatically handle building the project. Makefile's syntax is a bit obtuse, so let's walk through writing one. We start by defining a variable that holds our project name, then a variable that holds the desired output format, then one to hold the project's binary name, which will be the project's name with the .com extension. We'll define a variable to hold our assembler's name, the variable to hold the linker's name, then a variable to hold the assembler flags, which is just to output as ELF32, then a variable to hold the linker flags, which are to use a linker script with the same name as our project, and to link as ELF386. We'll define a variable to hold our source file names, and then we'll define the object files as a map of the source file names to the object file names. This syntax means to take every file name in the sources variable, and if the extension is .asm, change it to .o. So objects contains hello.o and rt.o. Editing note, this should be sources and not source. I'll end up noticing this in a few moments. And now onto the rules. The left side of the colon is called the target, and everything on the right side is called the prerequisites. All prerequisites will be satisfied before running the rule. We'll define a rule called all, which will build all of the targets we want to be built by default. It has a prerequisite on the project's binary. Then we define a rule to generate the project's binary. It has a prerequisite of the project's linked ELF file, and to output the binary, we'll have it run a tool called object copy to generate the binary from the linked ELF file. Then to generate the linked ELF file, we need the project's object files, and we run the linker with its flags, outputting to the ELF file and using the list of object files. Then we define a rule to generate any object file. The % sign is a wildcard. An object file needs its corresponding assembly file, and then we run the assembler with its flags, outputting to $@ symbol, which holds the name of the target, or the object file in this case, and then $ less than symbol, which holds the name of the first prerequisite, or in this case, the assembly file. Then we'll define a rule called clean, which removes all of the build artifacts. Editing note, here's where I get confused as to why the linker has no input files and figured out that I misspelled the sources variable in the objects map. If we run make clean and then make, we can see that it automatically builds everything for us and outputs an executable. We can then run object dump to see how the linker put the executable together. Wouldn't it be nice if we automatically generated the object dump? We can add another rule to the make file to make the dump and write it to projectname.list. If we add it to the clean target and then the all target, it'll be automatically generated for us next time we run make. If we look at the list file, we can see that there are these random exchange EAX instructions added after some of our functions. Like the stack segment, the i386 architecture definition defaults to the worst case alignment requirements for the fastest of the i386 architecture CPUs, basically the Intel Core Duo. These exchange EAX instructions are the official definition of what a no-op instruction is in 32-bit mode. And the 66 hex prefix is a special instruction prefix that lets you execute 32-bit instructions while in 16-bit mode if you're on a 386 or newer, so the linker uses NOP to pad out unused bytes in executable sections to make sure that if there's an error and the processor goes out of bounds, it isn't executing random garbage. We can get rid of most of this by going into our assembly and relaxing the alignment requirements on the text sections by specifying a line equals 4, which is perfectly fine on anything pre-Pentium. And even on the Pentium, it's just a performance optimization to align to 8-byte boundaries, as the Pentium had a 64-bit data bus. After changing the alignment, we can see that most of the padding has gone away and that our executable still behaves just as expected. Now that we can add source files to our program much easier, let's extend the functionality of our example a bit. Currently, we're just spamming our message to the console as quickly as it can print. How about we add a delay so that it only prints the message a few times per second? Let's create a new source file called time.asm and start a new 16-bit text section. As opposed to a modern operating system where we can just ask the kernel to suspend our process for a period of time, DOS is a single-tasking operating system. We're the only thing running, so if we need to stall for a period of time, it's on us to figure out when we're ready. So let's start with writing a function to get the current time, something like the millis function on an Arduino. Going back to the system call table, we see there's a function to get the current time from the system and return the time as precise as centiseconds, or hundredths of a second. As there are 360,000 centiseconds per minute, we'd exceed the limit of a 16-bit number, so let's just return a counter that rolls over every minute, or 6,000 centiseconds. So we call function to chex, and the time is returned in the cx and dx registers. To get centiseconds within the minute, we first need to multiply seconds by 100 to get centiseconds. Looking at the definition of the x86 multiply instruction, we see that for an 8-bit by 8-bit multiplication, the only thing we can do is multiply register AL by a register or memory location, and that the result will go into register AX. Unlike the other arithmetic operations we've used so far, multiply only works with register AX, and if you have a 32-bit result, register DX as well. Since the multiply instruction can't work with immediates, to multiply by a constant value, we first need to load our multiplier of 100 into register AL, and then multiply by the number of seconds, which is in register DH. Now we need to add the centiseconds from the current time, which is in register DL, to the AX register, but we can only add 8-bit registers to 8-bit registers and 16-bit registers to 16-bit registers. So we'll zero out the upper byte of the DX register since we're done with it, and then add DX to AX. When we return, the number of centiseconds within the minute will be in the AX register. Now let's write a function to wait for a period of time. We'll have it take the number of centiseconds to delay in register SI, then make a call to get centiseconds so we know when we first started to wait, and as register BX is the only one of the primary registers not used by get centiseconds, we'll use it to hold the start time. Now, we need to repeatedly call get centiseconds in a loop, while the current time minus the start time is less than the time we wanted to wait. And this is almost correct, but as the counter rolls over at 6,000, we need to check if that happened. If the current time wasn't greater than or equal to the start time, it would have rolled over, so we need to add 6,000 to correct for that. Then we add our new time.asm file to our make file, and then create a file called time.inc, which has the extern definitions for the get centiseconds and wait for functions we just wrote. Now we can include that into our main assembly file, and after the write call, we can set register SI to 20 to wait for 200 milliseconds, and then call the wait for function. A quick run of make, and then we transfer it to the board. And it looks like it's printing much slower. If we turn on timestamps though, the wait's not quite accurate. It always seems to wait a bit longer than 200 milliseconds. What's up with that? Well, in our implementation of wait for, we're always checking the time at the beginning and then waiting relative to that. So we spend at least the requested time inside wait for by itself, and we're not accounting for any time that passed between calls to it. What if we changed this to wait relative to a time provided by the caller that we advance between calls to wait for? Let's create a new entry point into this code called waitForBased, which effectively takes the base time in register BX. We'll just have the prior waitFor function fall into it in case we want to use it for something in the future. Quickly add waitForBased to our time.inc header, and then change our main function to call getCentiseconds at the beginning of the program. Since register DI is the only one we've not touched so far, we'll store the base time in there. Then copy register DI into BX before the call to waitForBased. After it returns, we advance register DI by however long we intended to wait for, and then check if it'll equal or exceed 6,000. If so, we need to subtract 6,000 to effectively roll the number over, and finally we just need to change the label we're looping back to. Now when we run the program, we can see that it waits an average of 200 milliseconds between printing our message. Sometimes it waits a little bit less, and sometimes it waits a little bit longer. If we wanted more accuracy out of the system, we'd need to take over one of the system's programmable timers, but that's quite a bit more complicated of a solution. This is perfectly fine for now. But printing hello world slowly isn't the most fun message in the world. DOS has a command called type, which prints the contents of a file to the console, but autoexec.bat isn't the most interesting thing to read. Let's grab a few paragraphs of lorem ipsum text from the web, paste it into a file, convert the line endings to DOS format, and then copy that over to our board. Now we have something fun to print. But it's kind of hard to follow the type command printing text, so what if we modified our timed hello world program to print the contents of the file, but slowly? A slow type command, if you will. We've been using a file handle to write text to the console, so presumably there'd be a command to open a file on disk as a new handle, right? Yep, we've got function 3dhex. Set register AL to 0 for read access, and DX to a 0 terminated string holding the file name. The carry flag will be set if there's an error, and AX will hold the file handle. Let's zero out register AL and set AH to 3dhex, and now we need a new string for the file name, which is ipsum.text, and remember to put a 0 on the end of the string to mark the end. We'll define a label for the length, although we're not going to need it. Set register DX to the string and call int21hex. Now let's jump to a new label called fail if an error occurred, and let's place it just before the return instruction so the error code is still in register AX. Now we need to read some bytes from the file to print. There's a function 3fhex to read data from a handle, and just like the write function, register bx is the file handle. Cx is the number of bytes, and dx is a pointer to the buffer. On return, register ax is the number of bytes read, or 0 if we hit the end of the file. The carry flag will be set if there was an error. So let's set AH to 3fhex and BX to the file handle. But unfortunately the file handle was in register AX, so it would have been overwritten by our call to get centiseconds, and it'll also get overwritten by later calls to our function, so we need to store it somewhere else. When you use a high-level language, you're used to having local variables you can store stuff in, but where do you put things in assembly? Well, those high-level languages generally store locals in something called a stack frame, which is memory the function reserves from the stack on entry. At this point, I've intentionally not touched register BP, which is commonly used to hold the stack frame pointer. So at the beginning of our main function, we need to push the previous value of register BP to the stack, which is our caller stack frame pointer, and then we store the current value of the stack pointer in register BP. As the stack grows downward, we subtract how much memory we want to reserve from the stack pointer. In our case, we want to store the 2-byte file handle, so let's subtract 2 bytes from the stack pointer. To store a file handle in the space we just allocated, we'll write it to memory location BP-2. But why the -2? Well, on x86 CPUs, the stack pointer points to the last written value. When writing a new value to the stack, the address is decremented before writing to memory. The address in register BP is the value of the stack pointer after saving the caller stack frame pointer, so BP actually points to that saved value. We need to decrement the pointer by 2 to find the new memory we allocated. So now we can load register BX from BP-2 to get the file handle, and let's say we'll read 4 bytes at a time from the file. Now we need to remember to clean up the stack frame we created before returning from the function. We do that by overwriting the stack pointer with register BP and pop the caller's value of BP back off the stack. And now we need a place to store the data we're reading from the file, so let's take another 4 bytes off the stack for a total of 6 bytes. We have to put the pointer to that into register DX, so we could set register DX to register BP and subtract 6 from it, but there's a better instruction for that. The LEA, or load effective address instruction, performs a requested address calculation and returns it into a register. So rather than reading the contents of BP-6, it returns the address of BP-6. Now we can finally call interrupt21hex to perform the read, and if the carry flag is set, we'll jump to the fail label. And if register AL is 0, we've hit the end of the file, so let's jump to a new label called done. Now that the number of bytes read is in register AX, we need to set register CX to AX before overwriting AX with the function to write to the console. Also, we can delete the previous calls that set up the message, and we don't need to worry about register DX because it's still set to the read buffer's address from the last call. Before we exit the program, we need to close the file. Checking the syscall table, we see that this is done with function 3e hex, with register BX set to the file handle. So we load the handle from BP-2 one last time and call function 3e hex. After assembling our program and transferring it to the board, it now prints lorem ipsum all nice and slow, although that doesn't fix it running off the end of the screen. And now that we're printing slowly, let's redirect the output to something a bit more fun, like this alphanumeric LCD. The slow type program is particularly useful here, as these types of LCDs have a slow pixel change rate. The BIOS only officially supports 40x2 LCDs, but this is a 20x4 LCD. While they both have the same number of characters, the controller, like the BIOS, is only officially capable of driving a 2-line display, so the organization of these panels is like a 40x2 LCD that you split vertically into two 20x2 halves and then stacked on top of each other. Let's write a quick batch script that calls the same int command we used earlier to toggle the onboard LED. A quick glance at the manual shows that we need to call interrupt 15 hex function B042 hex with register BH set to 1 to enable the LCD. So int A15 hex B042 hex 01 hex, and then use the console command to disable the serial console. Then we run slow type, and after that re-enable the serial console on COM2 and disable the LCD. Now we have lorem ipsum slowly printing out to our character LCD without having to change any of our program's code. You can also see how the organization of this display makes the text scrolling a tad strange. The computer doesn't buffer the screen, so when it sends a scroll command to the display's controller, the contents of lines 2 and 4 move to lines 1 and 3. So with all that, let's finally write the program that writes the poisoned CMOS data that'll cause the BIOS to wipe itself. Let's rename our program to destroy, and we don't need the time utilities anymore. Let's change our message to a warning about what the program is about to do, something like, are you really sure you want to destroy the BIOS? And let's also reuse the key press we previously used to exit the program as a confirmation of whether you want the program to proceed or not. We'll change it to abort unless you send a capital Y. Also, since these string labels denote the location of where the data begins, it's totally fine to do a multi-line string like this. The length calculation still works just fine. Rather than ipsum.text, let's load the poisoned CMOS data from cmos.bin. So now we can delete the call to get centiseconds as well as the loop label, and since we're no longer wiping out the register AX, we don't have to store the file handle on stack anymore. We can just move it to register BX before we set the function number for the read syscall. But now where do we store the data we're reading from the CMOS image file? We absolutely could just make space on the stack for it, but since this is a rather large blob of data, let's use a global buffer for it. One of the other program sections we've not talked about yet is the BSS section. This is used to store global variables that are all initialized to 0 by default, so we'll add a label for our CMOS data here. Checking the datasheet for the RTC module that's used on this board, we can see that it stores 114 bytes of data after the 14 bytes of control registers inside the module's 128-byte address space. So we need to make space to store a 114-byte image file. Since we're going to overwrite this with the contents of the file, we'll just tell NASM to reserve space rather than filling in 114 zeros, and also define a length constant. But as we've declared a new section, we need to add it to the linker script. We'll align it to 4 bytes like we did with the read-only data section, but seeing as we know that we'll be overwriting the contents of this data, it doesn't make any sense to include 114 bytes of zeros in the executable file. We can use an option called no-load that'll instruct the linker not to include any of the contents of this section in the binary file it produces, but it'll still compute addresses as if it did. With the way we've written this linker script so far, we need to make sure that we place the BSS declaration at the end of the script so we don't end up misaligning the load and run addresses of the other sections, but we can address this limitation in the future. We can also define symbols inside the linker script that'll help our program identify where things are. Let's mark the start and end location of the BSS section along with its size so we can have the runtime zero out the memory before doing anything. Switching back to the runtime source file, let's import the declarations for the BSS start and the BSS size variables, and then load the start into register DI, the size into register CX, and zero out register AX. Now, we could just call move in a loop to zero the memory, but we could instead use one of the more powerful features of these early x86 CPUs, the string instructions. Store string is a single instruction that will put the value of the accumulator into memory at the address held in register DI and then increment register DI. If we combine that with the repeat prefix, we can zero the whole BSS section with just 2 bytes of instruction opcodes and no jumps. But we can actually make this even faster. Our board's CPU has a 16-bit bus, so if we change this to the store string word instruction, we can zero out the memory 16 bits at a time, running twice as fast. We just need to change register CX to the size of the section in words rather than in bytes. So we'll just rename BSS size to BSS size words, and update the linker script to right shift the size by 1 to quickly divide it by 2. Back in our main function, let's make sure to update the size of the image file read to the size of the CMOS data, and change the read buffer pointer to the memory we just created in the BSS section. Previously, when we got a return code of 0 from the readsys call, it meant that we hit the end of the file and thus the program was done. But now if the return code isn't the image size we expect, that's an error. So we'll change this to a compare between the return code in the register AX and the read size in register CX. And if they don't match, we need to jump to an error handler. Also, since we don't need to read the file anymore, we should close the handler here. Admittedly, this program is supposed to wreck the computer, so we really don't care about file integrity, but hey, best practice is best practice. But on that note, if we failed to read the contents of the image file in the way we wanted, the handler is still open, so the failure handler we jump to should close it. Let's reuse the old done handler as the failed with file open handler, and we'll remove the zeroing of register AX so we return the error code from the program. We'll also change the write syscall to print out our confirmation prompt and remove all of the old timing logic. We also don't need to check if characters are waiting in the input buffer anymore, as the get character syscall will automatically wait for input to be available before returning, so we'll just remove that bit as well. Then we'll check if the character returned was a capital Y, and if it wasn't, jump to the failure handler. The file is closed now, so we can just use the simple one. And we'll also print out a message if the program failed or was aborted, just something simple like aborted. And now we're finally at the point where we can write out the poisoned CMOS data to the RTC module. Reading or writing it is a two-step process. First, you set the internal address by writing it to IO port 70 hex, and then you can read or write the location by accessing IO port 71 hex. This might sound like a strange design choice given that both the RTC and the 8086 had multiplexed buses, but in actuality the RTC wasn't standard equipment on PCs until the 286-based PCAT, which did not have a multiplexed bus. The RAM portion of the RTC starts at address 0E hex, so we'll start by loading that into register DI. We'll then load the address of the image data into register SI, and the length of the image into register CX. IO ports are accessed using special in and out instructions, and the only register that can be used with them is the accumulator, so we'll load the current write pointer into register AX, and then increment the pointer in register DI. Now we can issue the write to IO port 70 hex from register AL, setting the internal address of the RTC. Next, we need to load the next byte of the image data, and we'll do this with one of the string instructions. Load string reads the current byte pointed to by register SI into register AL, and then increments register SI. So we'll use load string byte and then output register AL to IO port 71 hex, writing the data to the location we previously set in the RTC. And finally, we'll use the loop instruction to jump back to write the next byte. The loop instruction automatically decrements register CX, and if it hits 0, it'll fall through rather than jumping. So we can use it to repeat a section of code a specific number of times without having to check a loop counter. As DOS might attempt to modify the contents of the RTC inside of an interrupt handler, we need to ensure that no interrupts will run while updating the RTC. So before the loop starts, add a CLI instruction to disable interrupts. So at this point, we've effectively put the system into an unstable state, so realistically the only thing we should do now is cause the board to reset. And here's where we diverge from the standard PC architecture. This board is based on a 386EX system on a chip, which contains a watchdog timer, which is a timer that will reset the hardware if it times out. They're used for automatically resetting a system if the software locks up, but we can intentionally turn it on and not clear the countdown to intentionally trigger a reset. This is actually documented in the board's manual. We just need to write some magic values to a couple of registers in the SoC. So let's add those registers as constants in an include file. To write to these registers, we again have to do something a little different. Reading or writing registers that have an address greater than 255, or FF hex, has to be done using indirect addressing, with the IO address being in register DX. So we'll just write out the magic values to the watchdog control registers, essentially using the pattern load register DX, load register AX, and then out DX AX. And now we assemble the program and copy it over to the board. Running it without hitting capital Y causes it to abort, but if we do give it a capital Y, it overwrites the CMOS data, triggers a reset, and we can see the BIOS reporting the wrong type of internal SSD. This is a TS3100, not a TS3200, and erasing the DOS and BIOS sections. The only reason the board is still up at this point is because the BIOS is shadowed into RAM, but if we tell the system to reboot, this board is completely and utterly cooked. The LED stays on, and as it stands, will never get output again. So now what? We have two options. The flash memory is unfortunately soldered to the board, so the first option would be to desolder the flash chip and reprogram it outside the system. Considering I already caused some damage to the board when removing the RTC module, I wasn't keen on removing something more complicated. Option 2 is to find some way to reprogram it in system, and there's solid proof that this is possible. The TS3200 manual has a few references to another product called the TS9500, and if we look at the manual for that, it mentions the ability to boot a BIOS image stored on the TS9500 itself rather than the one on the SBC, which means there must be some mechanism via the PC104 connector to override the onboard flash memory. The manual unfortunately doesn't mention how that works, so let's see if we can find anything interesting in the schematic. Starting with the PC104 connector, right off the bat there's already something strange going on. The I/O check pin is connected to the IRQ1 net on the expansion board, and over here we have DMA acknowledge 3 connected to one called UCS, and then DMA request 3 is connected to mainboard flash. I bet that's what lets the expansion board control the internal flash memory. Not sure how I feel about the violation of the PC104 specification, but that probably explains why the TS3200 manual makes a note that not only is DMA channel 3 unsupported, but also that expansion boards must not connect to it. Following those signals into the TS3100 schematic, DMA acknowledge 3 is still connected to the UCS net, and DMA request 3 is connected to the CS flash net. Canonically, CS means chip select, so that's definitely related to controlling the flash. We also have refresh connected to the CS0 net, so more violations. Jumping over to the flash memory, CS flash does in fact drive its chip select pin. But then there's this resistor connecting to a net called BUCS. Looking at some of the other signals nearby, we can see A0 to A19 go through some buffers and then turn into BA0 through BA19. So I'm guessing the B stands for buffered. Tracing the BUCS signal, it goes over to this Xilinx PLD, which connects to a substantial number of other nets. This is basically the board's chipset, and since it's a programmable logic device, we have absolutely no idea how it works. So we'll just have to make some educated guesses about its functions later. But there is that UCS net coming into it, and following that leads over to the UCS signal on the CPU. So the BUCS net is most likely defined by logic on the CPU rather than the chipset, but the fact that it does go through the chipset means we can't assume that it's only controlled by the CPU. But going back to the flash, the resistor between the BUCS net and the chip select signal is certainly interesting, and also that both sides of the resistor are brought out to the expansion connector. Oh, that's what they're doing. Okay, so the chip select signal is what's called an active low signal, meaning that connecting it to ground turns the chip on and connecting it to VCC turns it off. If we tie CS flash to VCC, even if the BUCS net goes low because the board is trying to enable the flash, it's not shorted out. Sure, you're wasting 5 volts divided by 680 ohms, so 7.5 milliamps of current through the resistor and PLD, but that's well within the rating of the PLD. The test circuit described in the PLD's manual is set up to source or sink around 10 milliamps, so we're good here. And since we have that UCS net on the expansion connector as well, we get the unmodified version even having tied the CS flash pin to 5 volts to disable the onboard flash. We can then connect that UCS pin to the chip select pin of an external memory, and the CPU will read from that instead of using the internal one, so let's do that. To make things even more fun, we're going to cram our recovery tool into this 8 kilobyte EEPROM, as it was the only non-volatile memory device I had when I first did this. These are accessed just like the onboard flash memory. They have 8 data pins to output the byte at whatever address is selected by the address pins. And in this case, there's only 13 of them, as this is an 8 kilobyte memory. 2 to the 13th power is 8,192. So we'll connect the write enable pin to VCC to disable writing, the output enable pin to the expansion connector's memory read pin, and the chip select pin to the UCS pin. Then connect up the address and data buses to the expansion connector, and finally remember to connect that CS flash pin to VCC and connect power to our external memory. As our memory is enabled by the UCS signal, we need to know when that signal is asserted. Heading over to the CPU's manual, the 386EX is basically a 386-based system on a chip. It bundles a 386CX core, which is a 386SX built on a static process, meaning that we can stop the clock or run it at very low frequencies without the CPU losing its internal state, along with the addition of the dreaded SMM mode and 2 additional address lines, meaning this processor can access 26 bits or 64 megabytes of memory. It has all of the standard IBM PC peripherals, serial ports, timer counter units, a DMA controller, the interrupt controllers, etc. It also has extended features like the chip select units, which reduce the need for external address decoding. For instance, this memory we're attaching. It has a JTAG unit for debugging, a watchdog timer, clock generation, a DRAM refresh controller, synchronous serial support, etc. Looking at the section on the chip select unit, it says that upon reset, the UCS channel is enabled for the entire address space of the processor and is configured for 15 wait states, which is good because this EEPROM has a 200 nanosecond access time. With the clock frequency being 25 megahertz or a cycle time of 40 nanoseconds, we certainly need a few of them. So at power up, all memory accesses will be directed at our little EEPROM. But where in the EEPROM are they going to go? Switching to the 386SX programmers reference, if we check the chapter on initialization and scroll to the section on processor state following power up, it says that the code segment register defaults to F000 hex, and the instruction pointer defaults to FFF0 hex. This means that the real mode or 20-bit address is FFFF0 hex, or 16 bytes away from the end of the address space. There's also a note that the invisible part of the code segment register holds FFFF0000 hex, so the actual address emitted from the CPU at reset will be all ones except for the last 4 bits, which will be 0. The invisible portion of the code segment register is part of protected mode, which we'll talk about in the future, but for now the important takeaway is that the code segment state at reset selects the last 64 kilobyte window at the end of the address space. This is actually different from the original 8086. While the address at reset is the same, on the 8086 the instruction pointer defaults to 0 rather than FFF0 hex, and the code segment defaults as all ones. This means that if the instruction pointer hits 16 or more, the final value will be greater than 20 bits and loop back around to the beginning of the address space, which would be well outside your ROM. The first instruction you need to run on an 8086 is a far jump to the beginning of your boot ROM, but on the 286 and 386, setting the code segment from real mode destroys that invisible portion, so you'd actually jump to the end of the first megabyte rather than the end of the entire address space. Unless you want to place your ROM at the end of the first megabyte, you need to be careful not to touch the code segment register until you're ready, and this is why the 286 and 386 changed the default register values. You can use a relative jump to go anywhere within the current 64 kilobyte segment without touching the segment registers. Now, because we're in the unique situation of having this upper chip select unit activate our ROM for the entire address space, this wouldn't actually be a problem, but it is something to note. To make sure our understanding of this is correct, let's try to write the most simple test possible to see if we're booting from the external ROM. As the symptom of something being wrong here was that the onboard LED stayed on, let's write a test that just turns the LED off. The schematic shows the LED being controlled by an active low signal called LED, which, if we scroll up a bit, is driven by the CPU's digital I/O port 1 pin 6. Checking the chapter of the manual on the input-output ports, if we look at the section on the reset state, we can see that P1.6 defaults to weakly pulled down, which, as the LED is driven by an active low signal, would cause the LED to turn on. So to turn the LED off, we need to configure the pin as an output and drive it high. Each port has a configuration register which determines whether each pin is either an I/O pin or connected to an internal peripheral, but that register defaults to all pins being configured as I/O pins, so we don't need to touch that for now. There's a register which controls whether the pins are outputs or inputs, and also a register which controls the value driven to the pin. So to configure P1.6 as an output, we need to set bit 6 of the port 1 direction register to 0, which is I/O address F864 hex. And to set the pin high, we need to set bit 6 of the port 1 latch register to 1, which is I/O address F862 hex. But before we can actually set values in those registers, we have to enable the expanded I/O address space of the processor. In the chapter on system register organization, it makes a note that a specific sequence of writes to I/O addresses 22 hex and 23 hex are required to enable access to the internal peripherals, and provide some sample code that we'll just lift into our program. So let's jump into the code. We'll use our previous example 6 as a reference and change the project name to recovery, and remember to change the project binary to a .bin rather than a .com, since we're just going to be flashing this to an EEPROM. In the new main.asm file, we'll start by setting up a constant for the port 1 latch register at F862 hex and another constant for the port 1 direction register at F864 hex. We'll create a new text section with 16-bit code and a label called boot. Here we'll copy the code from the manual that enables the expanded I/O address space. So to set the LED pin as an output, we'll set register DX to the address of the port 1 direction register. We'll get the current value of that register, then AND that value to BF hex to clear bit 6, and write that value back to the direction register. Now, to set the pin high, let's set register DX to the address of the port 1 latch register. We'll again get the current value of the register, then this time we'll OR it with 40 hex to set bit 6, and then write that back to the latch register. Now, in order to prevent the CPU from randomly running off somewhere, we'll add an infinite loop with a halt instruction, and that's the test. Now we just need a piece of code to jump to the boot label when the CPU resets. So we'll create another section called reset, again with 16-bit code, and all it'll do is jump to the boot label in the other section. Since this section is supposed to be the last 16 bytes of memory, we'll just pad out the unused space with zeros. Otherwise, the binary won't quite be the correct size. So we'll use the times statement to repeat zeros, 16 minus the quantity $sign minus $sign. $sign is the starting address of the current section, so we're doing the current address minus the section starting address, which gives us the length of the section so far, and subtracting that from 16 gives us the number of zeros to add to make the section 16 bytes long. Now we just need to edit our linker script and remove the old RO data and BSS sections and replace that with our newly added reset section. But now that we're running on Baremetal, we need to change the run addresses of the code. Since the EEPROM is effectively placed as the last 8 kilobytes of the 32-bit address space, before the text section, we can set the initial address to 1 left shifted by 32 minus 8,192, and before the reset section, we can set the address to 1 left shifted by 32 minus 16. To program the binary to the EEPROM, we'll put it in this TL866-2+ programmer I have, and use the MiniPro utility. MiniPro-P cat28C64B-U-W recovery.bin, and it wrote the binary. And if we plug that back into our board and apply power, hey, the LED shuts off. Look at that, we're loading from an external ROM. Well, I think that's a good place to call it for today. Next week we'll do platform bring up, essentially go through the processor's manual and figure out what we should set all these registers to. And since we still don't really know how this board's chipset works, we'll try using Ghidra to disassemble the BIOS image to see if we missed or misunderstood anything. So if you want to see that, just leave a like and subscribe so you don't miss the next video. Thanks for watching.